Hello, today we're going to do a basic derivation of Maxwell's four equations, which are the fundamentals of electricity and magnetism. We know from my video on electromagnetism that if we have a point charge, let's call it Q, and let's say it's a positive charge, then the electric field will radiate from that charge radially, in all directions equally. And we know that if we bring another charge, let's call it a test charge little q, into the vicinity of capital Q, there will be a force between the two charges, which is known as the Coulomb force. And that is given, as we showed in the previous video, by QQ over 4 pi epsilon r squared, where epsilon is the permittivity of free space. And I also said that the field strength at any point is given by Q over 4 pi epsilon r squared. Now, what is field? What is the electric field? Well, it's the capability at any point to do something. In other words, it's the capability to exert a force on a charge if there were a charge there. So if you were to put a charge, say plus Q, little q, at this point here, then you could work out what the force would be, because the force would simply be the electric field times Q. So in other words, the electric field is essentially force per unit charge. And force is always measured in newtons, and charge is always measured in coulombs. So the value of the E field, the electric field, is measured in newtons per coulomb. I now want to consider the concept of electric flux. Flux is simply the amount of a field that goes through a particular area. So if we take our charge, again, which radiates outwards, E field going in all directions, and we want to know how much of that field goes through an area, or a window if you like, of area dA, so it's a small window, dA, then we say the flux, which is represented by the Greek letter phi, the amount of flux that goes through the window will only be a small amount of flux, so d phi is equal to the amount of the field, which is the value of the field at that point, E, times the area, dA. So it's as simple as that. Flux is the field that goes through the area. But mathematically, it is written in this form, E dot dA, and a dot is a vector product. And it is also equal to E times dA times the cosine of theta. And let me explain why we need that cosine term. You see, it all depends on the angle that the flux, or the E field, meets the window. Let's suppose that this is the E field in this direction. If the window is square on, in other words at 90 degrees, then the E field will pass through the window. If on the other hand the window is flat on, then no flux will go through the window, it just bypasses it. So the critical thing is, what angle is the window to the E field? And that's where this cos theta term comes in. And what theta is it is the normal to the window, the angle between the normal to the window and the E field. So this is the E field. This is the normal to the window, in other words 90 degrees to the plane of the window. And theta is the angle between the two. And when theta is equal to 90 degrees, cos theta is equal to 0. So this whole term becomes 0. And so the flux going through the window is 0. When the angle between the normal, which of course will now point in that direction, and the E field is 0, cosine theta will be 1, and so you now get maximum flux, EdA, passing through the window. So now let's consider a charge. Once again, it's a charge Q, and we're going to construct around it a sphere. Now, this is not a metal sphere. If you like, you can regard this as an imaginary sphere, or if you like, a sphere made out of plastic. So it's just a sphere around the charge, and the sphere has a radius r. Well, if you ask yourself what is the amount of flux passing through an area dA on the surface of the sphere, then the answer, of course, we've just derived is that the flux going through that little window will equal E times dA. We don't have to do dot dA in this case because, of course, we know that the field will always go out radially, and we know that the radius of a sphere always meets the surface of the sphere at 90 degrees. So you're always going to get maximum flux through a window which is on the surface of the sphere. And so if you integrate this to find out the total flux going through the entire sphere, you get that phi, total flux going through the entire sphere, is the integral of E dot dA, and that is E times 4 pi r squared. Since, as I've said, you don't really need the E dot dA, it's E dA because the cosine term will automatically be 1. But right at the beginning of this, we showed that E is equal to Q, the charge, divided by 4 pi epsilon r squared. And so if we substitute that for E in this equation here, we get that the total flux is equal to E, which is Q over 4 pi epsilon r squared, times this term here, 4 pi r squared. And you'll see that the 4 pi r squareds cancel out, leaving you with Q over epsilon. So the total flux passing through the entire surface of this sphere is equal to the charge divided by a constant, which is the permittivity of free space. If there were another charge in this sphere, then the total flux would be the flux due to this charge plus the flux due to that charge. And that means that where you've got more than one charge, the total flux will equal sigma q, the total charge, divided by epsilon. And so we can say that phi is equal to, well, it's equal to the integral of E dot dA, over the entire surface of the sphere, and we show that by putting a little ring there. That means over the surface of the sphere, the whole surface, is equal to sigma q over epsilon. And that is known as Gauss's law, and it's also Maxwell's first law. So Maxwell actually borrowed, as we shall see, 3 of his 4 laws are down to other people. This is the first, and it's Gauss's law. One obvious point, suppose you were to put a charge of plus q and minus q inside the sphere. Then according to Gauss's law, the total flux would equal sigma q. Well, plus q and minus q come to 0. That means the total flux would be 0. Does that mean there's no E field? No, it simply means that the amount of flux going out from the positive charge will be balanced by the amount of flux coming in from the negative charge. So the net flux, which is what this is all about, the net flux passing through the surface of the sphere would be 0. Now, before we move on, I want us to look at 1 or 2 interesting consequences of Gauss's law. Let's take this time we're going to take a metal sphere, and on that sphere we are going to place the charge Q. And of course the charge will simply distribute itself right the way around that sphere evenly, because the sphere is a metal sphere, so electrons are free to move, charge is free to move, and consequently because it will be all this positive charge will be repelling itself, it will try to get equidistant from all the other charges, so that there is no potential to move, and all the charge will then be equidistant. And what I want to know is, what is the electric field at a point A outside the sphere, and what is the electric field at a point B inside the sphere? Well, Gauss's law tells us that I can construct a sphere. This is the sort of the imaginary sphere, or if you like, the plastic sphere, around the charge, in such a way that A, the point that we are interested in, is on that sphere. And the total distance from the centre of the sphere is, let's say, R. Now, what does Gauss's law tell us? Gauss's law tells us that the amount of flux which passes through the surface of this large sphere here is going to be equal to the integral of E dot dA, that's the electric field through the total surface area of the sphere, and that will equal sigma Q over epsilon. That's Gauss's law. Well, what is the sigma Q for this sphere here? It's the charge enclosed, the charge within the sphere. What is the charge within the sphere? It's plus Q. So that is simply Q over epsilon. EdA, as before, the integral over the whole of the surface of the sphere, will simply give you E times the surface area of the sphere. E times 4 pi r squared equals Q over epsilon, which means that E is equal to, we'll divide both sides by 4 pi r squared, Q over 4 pi r squared epsilon. And that is the value of the field at point A. But look, that's rather interesting, because that is exactly the same as the value of the field would have been if that entire charge had been at the centre of the sphere. So that if this charge, instead of being distributed on a metal sphere itself, had all been collected at a point at the centre, then the value of the field at A would have been this value here. So what Gauss's law tells you is that if you've got charge distributed on a sphere, outside that sphere, beyond that sphere, the electric field strength will be exactly the same as it would have been if all the charge had been accumulated in a single point at the centre of that sphere. Now let's look at the consequence of being at point B, in other words, inside the sphere. Well, once again, Gauss's law tells me that I can construct a sphere, and I've got exactly the same formula again, that the flux is going to be the integral of E dot dA, which is going to be sigma Q over epsilon. And Q has got to be the total charge within the sphere. Well, how much charge is there inside this sphere? The answer is none. All the charge is on the surface of the metal sphere here. There's nothing inside this sphere here. And that means that E dot dA is equal to the sum of the charges, which is 0. So E dot dA must be 0, which means that E must be 0, since the total area of the sphere is not 0. So E must be 0. So for point B in this sphere, point B, the electric field is 0. And what that tells you, Gauss's law is telling you that if you've got charge on a sphere, inside that sphere there is no electric field at all. Which means that if you were to put, say, an electron there, it wouldn't move, because there's no E field, there's no force acting on it. You might at first sight think that because the electron is much nearer this part of the sphere, that the electron would be attracted to this bit of it. But the point is that although there is a very close charge on this bit of the sphere here, there is a much greater charge on the other side of the sphere, but it's further away. And the effect is they cancel each other out. So that within the metal sphere, there is no E field, which means there's no force to act on any charged particles. Any charged particle inside a metal sphere on which a positive or indeed negative charge has been placed will not move, because there'll be no E field acting on it. Okay, let's move on. And we're going to do exactly the same thing as we did for Maxwell's first law, but this time we're going to consider not an electric charge of Q, but a magnetic charge or a magnetic pole. And what we want to say is that if we construct a surface and we have within that surface some kind of magnetic pole or magnetic charge, if you like, what is the equivalent formula to Gauss's law, which we had up here? Phi is equal to the integral of E dot dA, which is equal to sigma q over epsilon. Would we expect to get a similar kind of formula? Well, let's write down what that similar formula would be. We would say that the magnetic flux, which we'll call phi b, is equal to the integral over the whole of the surface of B dot dA, where B is now the magnetic field, and that's going to be sigma, the total amount of magnetic charge, or the total amount of magnetic poles, if you like, divided by some constant k. It won't necessarily be epsilon, because epsilon applies to electric fields. So we're looking for something along those kind of lines to equate to Gauss's law in relation to electric fields. Well, the answer is that this term will always equal 0. And why is that? Because you can never have just a North Pole or just a South Pole. In magnetic terms, a North Pole is kind of equivalent to a positive charge, and a South Pole is kind of equivalent to a negative charge. But you can never have one without the other. If you put a magnet in here, it will have a North Pole and it will have a South Pole. And consequently, that's exactly the same in principle as having a plus Q and a minus Q. When you do the sigma Q plus minus Q is 0. You will always have the same strength North Pole as you have the opposite strength South Pole. Consequently, this term will always be 0. So now you've got that phi b is equal to the integral of B dot dA, which equals 0. And that is Maxwell's second law. And that says that the total flux, the total magnetic flux passing through a surface of a sphere will always be 0, because there's as much negative as there is positive, the equivalent of, there's as much magnetic flux going out of the sphere as there is magnetic flux coming in. There will be magnetic flux going out as a consequence of the North Pole, but there will be magnetic flux coming in as a consequence of the South Pole. And the two will balance one another out, so the net flux will always be 0. You might think that you can cheat. You might think that if you take the surface of the sphere, you could put a bar magnet like this, where the North Pole is inside the sphere and the South Pole is outside the sphere. And now you've got a North Pole within, but a South Pole outside. And surely that will violate what we've just done. Well, unfortunately, of course, it violates the very principle that the sphere has to be a closed sphere. It has to be an entire sphere with no holes in it. If you put a bar magnet across the sphere, you have broken the sphere. It's no longer a complete closed sphere, and therefore it won't apply. All sorts of funny things will happen. So this is not allowed. You have to play by the rules. The magnet has to be wholly within the sphere, and if it is, then you will have a North Pole and a South Pole both inside the sphere, and that means that you will have a net flux, a net magnetic flux passing through the surface of 0. That's Maxwell's second law. We now move on to Maxwell's third law, and for this we will consider a coil of wire. Okay, it's just a plain coil of wire, and we're going to take a bar magnet, north-south, and what we're going to do is we're going to push that bar magnet in and out of the coil. So we're just going to change direction, move it in, move it out, move it in, move it out. And what we know is that when you have a magnet moving inside a coil, a current will flow. The direction of that current, of course, will keep changing. It will go in one direction when you push the magnet in, and it will come out in the other direction when you pull the magnet out. But the current will flow when the magnet is moving. If you simply hold the magnet steady inside the coil of wire, nothing happens, no current flows. It's only when you move the magnet that the current flows, and that is because you've got an induced current, and the induced current arises because of the change in the magnetic field. And the faster you move the magnet in and out, in other words, the greater you change the field, the greater the rate of change of field, the greater the current will be. And if there is a current flowing in this coil of wire, it must be the case that there is a voltage difference, a potential difference, what we call an EMF, the electromotive force. It's got nothing to do with force at all, it's a voltage, it's a potential difference causing the current to flow. And so what we can say is that the electromotive force, which is of course the EMF, which is a voltage, which is driving the current, is going to be, well, it's going to be proportional to the rate of change of the magnetic field. The faster you move the magnet in and out. By experiment, you can also find that the EMF will be also proportional to the area of the surface, that is this, essentially this surface here, that is the open surface which is surrounded by the current loop. And so you can also say that E, the EMF, is proportional to A, the surface. And so we can say that the total EMF is proportional to the change of the magnetic field times the area. Now, the definition of flux, we've already established this, is the amount of the magnetic field or electric field, as the case may be, going through a particular area. So flux is equal to B, in this case it's magnetic flux, times the area, and it's a dot product, remember, because of course it critically depends whether the window that is the area you're putting the flux through is, as it were, at 90 degrees to the field or not. So if phi, the magnetic flux, is equal to B dot dA, then d phi by dt is going to be dB by dt dot dA. But we know that dB by dt times the area is equal to the EMF. And so now you've got that the EMF is equal to d phi by dt, and that is equal to d by dt times B dot dA. So what this is telling us is that the EMF, the electromotive force, is equal to the rate of change of flux, which is itself equal to the rate of change of B dot dA. We'll park that formula. We will need to come back to it, but we'll park it. We're not yet at the third law. We now need to use Maxwell's first law, which was Gauss's law, to get us a little bit further along the road. And what we're going to do is we're going to consider two large parallel plates, metallic parallel plates, if you like, a very, very large capacitor. The reason it has to be large is that we're interested in what's happening away from the edges. So there will be edge effects, but if you get far enough away from the edges in the middle, then the edges don't have very much impact. And what we want to ask ourselves is let's just consider the surface of one of those plates, and on that plate there will be a charge, and we're going to say that the density of that charge, or the charge per unit area, is sigma. So it's the amount of charge in a particular area is sigma, and the total charge will of course be sigma times the entire area. Now, Gauss says I can construct a surface beforehand we constructed a sphere. It turns out it doesn't have to be a sphere. It can be any surface. So we're going to construct a surface which is essentially a cylinder, which straddles, as it were, the metal plate, so that H is above the plate and H is below the plate, and the radius of the cylinder will be R, so the diameter will be 2 times R. And Gauss's law, you'll remember, tells us that E dot dA is equal to sigma q over epsilon. That's Gauss's law, the first of Maxwell's equations. Now then, what will the electric field do from a plate which has got uniform charge on it? Well, the field will always come out from a plate at 90 degrees to the plate. It can't go in that direction because there'll be another, if it did, there'll be another charge going in that direction, and the net resolution of the components of these fields would be out at 90 degrees. So the field always leaves at 90 degrees. So how much field goes through the sides of the cylinder? Answer none, because it's all going parallel and it won't go through the side of the cylinder. So the only flux goes through the top and the bottom of the cylinder. So the flux that passes through, which is E dot dA, is going to be the total charge within this cylinder. And so now you've got that E times dA, well, there's two areas that the flux will go out from. This area at the top of the cylinder, this area at the bottom of the cylinder. Each of them is pi r squared, and so the total area is 2 pi r squared, top and bottom. So that's E dot dA. And the flux, of course, is going out at 90 degrees to the surface, so we don't really need to worry about the dot term. What is the charge within that cylinder? Well, it's going to be the charge per unit area times the area. Well, the charge per unit area, we've said, is sigma, and the area is going to be pi r squared, because that's the area of the charge on the plate inside, it always has to be inside the surface, inside the cylinder, divided by epsilon. Well, if you now divide both sides by pi r squared, you will get that E is equal to sigma over 2 epsilon. And that's a rather interesting result, because it tells you that the field anywhere above or below the plate is going to be equal to sigma divided by 2 epsilon. And the fascinating thing about that is that that is completely independent of H. You'll notice H doesn't feature at all. So the field above a very large plate, remember this has to be a large plate, if you get anywhere near the edges this no longer applies, but the field above a plate will always be sigma over 2 epsilon, however far you are above the plate. So now we consider the position where you have two plates and a difference in charge. Let's say we put plus Q on that plate and minus Q on that plate. What will the effect be? Well, let's consider firstly just the top plate. That will have an E field which goes out from the plate. The E field always goes out from a positive charge. And remember, it's constant in space. It doesn't vary. So there will be an E field going in that direction. There'll be an E field going in this direction and an E field in this direction, all due to this plate here. All of those fields, and they will be constant, the same, in all points, due to this field here. Sorry, due to this plate here. What about this plate? This has got a negative charge on it, so the fields will go into the plate, which means that there will be a field going into the plate there. there will be a field going into the plate there and a field going into this plate here. Remember, it doesn't matter how far you go above the plate, the field strength remains the same. It's what we just showed here. So what does that tell us? Well, if you look at the effect of the two plates, outside this field will cancel this field. So outside at the top, E will be 0. Similarly, underneath the two plates, this is going in this direction, this is going in the other direction. The consequence is that the E field will be 0 outside at the bottom. But inside the plate, you've got two E fields both pulling in the same direction. And since E is sigma over 2 epsilon, that means that the total field inside the plates will be equal to sigma over epsilon, just double this value here. Now I want to consider what voltage actually is. Voltage is the potential energy acting on a charge to move the charge from one point to another point. Technically, if you have a charge Q, then the voltage is the work done to bring a test charge, little q, from infinity all the way in to a point which is a distance r away from the main charge Q. So the voltage is the work done to bring this test charge from infinity to this point. And that then becomes essentially the electric potential per that unit charge. Well, what is potential energy? That is the work done, which is equal to the force times the distance. What is the potential energy at infinity? The answer is 0. If you look, you ask yourself, what is the force between these two charges at infinity? Well, the force, as we saw right at the beginning, is going to be q over 4 pi epsilon r squared, where r is now infinite because it's the separation of the two charges. And when q is at infinity, in other words, infinitely far from capital Q, then r squared, infinity squared, is going to mean that the force is 0 because you've got an infinity squared term in the denominator. So there's no force. What is the force when you get to the point where q is separated by little q by a distance r? That force will once again be equal to q over 4 pi epsilon r squared, where r now is just this distance here, and the potential is going to be the work done, which is the force times the distance. So we now have to multiply that by r, and that gets you q over 4 pi epsilon r. And that's going to be the potential energy, the force times the distance. But voltage is potential energy per unit charge. So it's potential energy divided by the unit charge. And so voltage is going to be Q over 4 pi epsilon R. But let me just remind you that the E field, as we defined right at the beginning of this video, is Q over 4 pi epsilon R squared. So that gives us a very easy relationship between E and V. It's simply that V is equal to E times R, or E equals V over R. And just to notice that earlier on in the video we said that E, the E field, could be measured in terms of newtons per coulomb because it is force divided by charge. Now you'll see it's also volts divided by distance. So E is not only newtons per coulomb, it's also volts per meter. You can express the E field in both ways. So now if we go back to our parallel plates, where you remember the E field between the plates is the same everywhere, then what you can say is that there's a voltage difference, V, let's say that that voltage is 0 and we've got a voltage V on this upper plate, the electric field will be the same everywhere, but the voltage will vary according to the distance from this plate. So halfway up, this will be V over 2, because E is V over R. So the greater the distance, the greater V will have to be in order for E to be a constant. So we've established this general principle for large parallel plates, that within those plates the electric field is constant, but the voltage has to change as the distance increases. Now, as a general point, you can say that even when you haven't got parallel plates, even if you've got just a coil of wire, if you break that coil up into very small distances, which have a distance dl, then the same principle that we've developed up here will apply, which is that V is equal to the E field times the distance, which means V, which you can also write as the EMF, is equal to the E field times the distance. And once again, to get it mathematically correct, it's actually E dot dl, because you have to take account of the difference between the E field and the direction in which dl is pointing. And so we've now got that the EMF is E dot dl, which means that the total EMF will be the integral around the wire. So the total EMF is going to be the integral around the wire of E dot dl. And now, having done that excursion, we can go back to the equation we derived before, where we said that the total EMF is equal to the rate of change of flux, and we said that that was the same as the rate of change of B dot dA, but we've just said that E is also the integral of E dot dl. And of course, these terms also have to be integrated if you want to integrate the full terms. So the total EMF is the integral of the rate of change of flux, which is also the integral of the rate of change of B dot dA, which is also the integral of E dot dl. And that is what is known as Faraday's law, and is also Maxwell's third law. And just to rehearse what it says, the total EMF will be the rate of change of B dot dA over an open surface, and that is equal to the integral of E dot dl over a closed loop. Just to remind what we're talking about, remember we started off with the idea of a loop of wire, and we have a magnet which we are moving in and out of that wire. That magnet creates a changing flux, and the integral of that flux going through the area, that is this that open surface, that's this surface here, the integral going through that surface, which is this term here, is equal to the integral of the closed loop, that is this loop here, of E dot dl. So the magnetic flux going through the surface, which is essentially that term, is equal to the electric field round this closed loop. And that's what's called Maxwell's third law and Faraday's law. And it may look a bit odd, but as many people point out, that is the formula which runs the entire economy, because that's the basic formula that describes how power stations work. When steam drives turbines, the turbines have effectively coils of wire which spin in a magnetic field. It doesn't really matter whether it's the magnet that's moving or the coil of wire that's moving. A moving coil in the presence of a stationary magnetic field, or the other way round, will cause a current to flow. And that is how electricity is generated, and that's the formula that governs the generation of electricity. That is Maxwell's third law. And now we move on to Maxwell's fourth and final law. And here we are considering a current which is flowing in a wire which is going essentially into the paper. And you demonstrate a current flowing into the paper by using a cross. If it were coming out of the paper, you would use a dot. It's rather like an arrow going away from you. You see the tail feathers, the cross. If you see an arrow coming towards you, you just see the point of the arrow. So this indicates a current flowing into the paper, in a wire that's going into the paper. And experimentally you find that around the wire you will get a magnetic field, B. And again, experimentally it is shown that value of the magnetic field will be proportional to the value of the current. The greater the current, the greater will be the magnetic field, divided by R, where R is the distance from the wire to the point at which you're measuring the magnetic field, and that is an inverse term, which means the further you get away from the wire, the smaller the magnetic field will be. Whenever you have a proportional term, you can always put a constant in, and so what we say is that B is equal to a constant, and the constant is called mu0 over 2 pi times I divided by R. Mu0 is what is called the permeability of free space, not the permittivity, that was epsilon. This is the permeability of free space, and this formula here is essentially a formula that was derived by Biot-Savart, sometimes called the Biot-Savart law. Now once again, much as we did for the third law, we can take this closed loop and we can break it down into lots of different segments of length dl, and we can ask ourselves, what is the value of B dot dl over the entire closed loop? Well, the value of B dot dl over the entire closed loop. Well, that will equal B times the value of dl over the entire loop. Well, the value of dl over the entire loop, of course, is 2 pi r, the circumference of this circle. So that's 2 pi r. But B is mu0 over 2 pi times I over r. So this is equal to B, which is mu0 over 2 pi times I over r, that's this term here, times 2 pi r. And you'll notice that the 2 pi r cancel out. And so now you get the interesting result that the integral of B dot dl, that is around this closed loop, is equal to the permeability of free space times the current passing through the wire. And that is almost Maxwell's fourth equation. It's also called Ampere's law. So you can see Maxwell got his first law from Gauss, his third law from Faraday, and his final law from Ampere. But we're not quite there because of a technical twist, and it's this. What we're saying is we've got a current in a wire which is going through this surface. It's going into the paper through the surface. And we're looking at a closed loop around the wire. And we need a proper technical definition of what we mean by the current going through the surface. The surface which is attached to this closed loop. And the question is, does it have to be a flat surface, as it is on this piece of paper? You know, here is the closed loop, and the flat surface is my piece of paper, and the wire penetrates the paper, or penetrates the surface. That's clear. But does it have to be a flat surface? And the answer is, no, it doesn't. It could, for example, if this is the closed loop, in other words, that is this loop, but edge on, you could attach a surface which represents essentially a bag. So this is just a bag attached to this loop. Provided the current flows through and comes out of this surface, there's the current I, then this formula is applicable. So the surface doesn't have to be a flat surface, in other words, it doesn't have to be just that surface there, it can be a bag, as long as the wire carrying the current penetrates the surface. then this is the closed loop and this is the open surface. And that's what gives us the problem. Because let's suppose we've got a wire. Fine, so far it's got a current I. And let's suppose that we're measuring the magnetic field around this closed loop here. Fine, you would say still no problem, this formula is going to work. But let's suppose we have a capacitor here. And let's suppose the capacitor is still charging, which means the current is still flowing. Well, what happens if I do this trick and put a bag, in other words, an open surface which doesn't have to be flat, such that the bag does this? Now you say, does the current penetrate the surface of the bag? And the answer is no, it doesn't, because no current flows between the plates of a capacitor. So you're stymied. You'd have to say no current flows, and therefore the total B dot dl is going to be mu0 times naught, which is naught, which means that you would not expect to find a magnetic field at this value at this point on the closed loop, which is madness. Of course there will be a magnetic field there. So we've got to have some kind of corrective term which we add to this equation here. And how are we going to do that? Well, here we've got the key term is mu0 times I. So let's write that down. That's the term that we want inside this capacitor here, because that's what's causing us all the trouble. And what can we say about mu0 I? Well, current is simply the rate of flow of charge. That's its definition. So I is equal to dq by dt, the rate of flow of charge. That's what current is. Now you can always multiply a formula by the same values as long as you do top and bottom, because essentially that just means you're multiplying by 1. So I am going to multiply by, I'm going to take mu0, and then I'm going to multiply by epsilon dA divided by epsilon dA, that's just 1, so I've done no damage to the formula, times dq by dt. Let me just show you what I've done. I've taken mu0 dq by dt, that's mu0 dq by dt, and then multiplied it by 1. Epsilon dA divided by epsilon dA, that's 1. I've done no damage to this term at all. But now I can rearrange that mu0 times I is equal to mu0 epsilon dA times d by dt q divided by epsilon dA. But let me just remind you of Gauss's law, which is Maxwell's first law, which says that E dot dA is equal to Q, or sigma Q, divided by epsilon, which tells us that E is equal to Q divided by epsilon dA. And Q divided by epsilon dA is this term here. And so now we can write this term as mu0 epsilon dA times d by dt times E, the rate of change of field with time. But I can go further. I can take this dA term and bring it here. So we now have mu0 epsilon d by dt E dA. And what is E dot dA, or EDA? That, of course, is flux. And so we now get that this term, mu0 I, is equal to this term here, which is mu0 epsilon d phi by dt. Rate of change of flux. And just to remind you that since it came from an E field, it is effectively electric flux, not magnetic flux. And this is often called the displacement current. That's its technical term. It's when you've got this situation where you've got a capacitor, no current is flowing, there is a kind of an implied or displacement current, and that term has to be added to this term, and that gives you the grand final term that the integral of B dot dl around the closed loop of wire is equal to mu 0 I, which is the formula we had up here, and applies if you haven't got this capacitor in the way. But if you've got this capacitor problem here, you also have to add this displacement current here, which is mu 0 epsilon d phi, and just put an E there to tell you that it's an electric field, d phi by dt, and that is Maxwell's fourth law. There's just one final point to mention, which is a point of intrigue, and that was this term here, the permeability of free space multiplied by the permittivity of free space. Maxwell discovered that mu 0 epsilon equals 1 over c squared, where c is the speed of light. And so he discovered that there were two terms associated with electromagnetism, which when multiplied together related to the speed of light. And that's what gave Maxwell the concept that there was an eternal speed limit, or a universal speed limit, the speed of light, c squared, which is now related to electromagnetic terms. And from this, Maxwell was able to deduce that light was electromagnetic radiation. But that's for another video. So for completeness, now let's just write out Maxwell's four equations so we know what they say. The first equation says that the total flux is the amount of electric field going through the area, which is the integral over a surface. It doesn't have to be a spherical surface, it's just the integral over a surface, and that will always be the total charge contained within the surface divided by the permittivity of free space. That's the first law. The second law does the same thing for magnetic flux. So this was electric flux, this is magnetic flux, and that is the integral of B dot dA, the magnetic field going through an area over an entire surface, is equal to 0. And we said it was 0 because you can't have a north pole without having a south pole. Then we came to Maxwell's third law, which is also Faraday's law, which says that the total integral of the change of flux, rate of change of flux, is equal to the integral of E dot dl over a closed loop, that's the field times the distance, which is equal to d by dt times the integral over the open surface of B dot dA. And that's Maxwell's third law. And then, as we've just derived, Maxwell's fourth law says that the integral over a closed loop of B dot dl is equal to mu 0 times I, which for most times is sufficient, that will work, but where you've got that capacitor problem, you also have to recognise that there will be a displacement current, mu 0 epsilon times d phi e by dt. So when that term is 0, which it will be if the surface goes through between the capacitor plates, this is the term which will enable you to calculate the magnetic, the B dot dl term, that is the changing flux. And those are four basic derivations of Maxwell's equations. They can be put together in a more vector form, but I just wanted to do a basic derivation for the purposes of this video.